Okay, we had talked about traditional fossil fuels and as well as the unconventional shale oil and shale gas. Uh, we didn't talk about oil shales, and that's a little confusing. An oil shale is not a shale oil. Um, we talked about shale oils, and shale oils basically have matured, but they haven't migrated. Oil shales are organics that haven't really matured very much. They're very sticky bitumen, and as a result, they also haven't migrated. But there's a lot of them. And in particular, when we look at the Green River oil shales and associated areas, uh, the USGS predicts there may be 1.5 or 2 trillion barrels of in situ oil. That doesn't mean it's recoverable, but one estimate is maybe 800 billion barrels. So there's a huge amount of oil, and it's largely on federal lands, which has some advantages and disadvantages, but it makes the regulations concerning the development a little easier to handle. Now, it turns out that Exxon was involved in it. In fact, I should even add that in 1974, I had a professor say that as soon as gasoline reaches 50 cents a gallon, these oil shales will be profitable. Well, of course, what he didn't predict was that as the price of oil goes up, so does the price of everything else, including the development of these oil shales. Well, Exxon started to look at the increase in price of oil, and they spent $5 billion in the 1980s basically on the assumption that they would do strip mining. Now, the problem with the strip mining, besides the economics, is that there are extensive environmental issues. It uses a huge amount of water, or rather the refiner uses a huge amount of water. It generates a huge volume of material. Literally, after you've roasted this stuff, you've got more material left than you do coming in, and it's very energy intensive. Well, Exxon basically lost that money and walked away. Okay, this was in the 1980s. Well, in the 1990s to early 2000s, we began to look at in situ ways of developing the oil shale. An ICP is an in situ conversion process. And Shell developed an idea that said, we're going to put an ice curtain. We're going to freeze the perimeter of this area, and then we're going to pump in heat. And so we're going to pump in steam heat in these wells, and basically the area that is confined within this ice curtain will then get low enough viscosity to be able to be produced and then refined. Okay. Now you might have to heat it a long time, 2 or 3 years, but that was their approach, and it required a lot of heat, and therefore electricity. So you used a lot of energy to get the energy. Used about a unit of energy for every 3.5 units of energy produced. Well, that's actually maybe a little better than the oil sands, which was maybe 2 to 1, but that is 1 unit of energy for every 2. I've inverted that. But for conventional oil, it's 1 unit of energy for 20. So there is this issue of energy efficiency. But nonetheless, Shell thought this would be economic at $30 a barrel. Well, apparently not, because in 2013 they abandoned it after, again, putting in millions of dollars into exploration. And basically they said that since the project started in '82, they weren't going to continue to do it. It just, the market had changed. And part of the change in the market is not only that the price of oil is volatile, but also the price of competitors is getting more difficult to deal with if you are an alternative form of energy. The increased presence of shale oil and shale gas just makes oil shale not energy effective, or rather not cost effective. And there continue to be environmental problems, largely because these areas where the oil shales are preserved, and these are our old Cretaceous age lacustrine deposits, they're basically in the arid west, yet it needs a lot of water. And so the water is perhaps the biggest drawback, as is the energy efficiency. I was going to do a thing on coal bed methane. It produces a lot of air pollution, water pollution, ground subsidence, etc. But then I saw this and I thought, why bother? Essentially, the future, at least as predicted by the Department of Energy, is that coal bed methane just is not going to be a player in the foreseeable future, mainly because of the environmental constraints. Okay, so we're going to ignore it, but recognize that on the list of alternative fuels, that's going to be one that you'll see. Also on the list of alternative fuels are gas hydrates, and these are literally methane that is trapped within an ice structure. What you see here is a burning piece of what looks like ice. Well, there's a huge, just absolutely huge resource sitting here of gas hydrates, twice the size of all the fossil fuels in the globe. The problem is it's just not, one, it's not nearly economic. And it's probably not economic for the near foreseeable future. And one of the problems with hydrates is that they are basically, when they melt, they produce the methane. Well, that's actually good in a way, but a lot of the hydrates are sitting either in the ocean, in the deep ocean where it's quite cold, or it's trapped in permafrost in the northern areas. And so one of the concerns about global warming, both with respect to the rising sea level and covering permafrost in the Arctic and simply melting the Arctic, is that that methane that is a tremendous resource also becomes an air pollutant. And so ironically, one of the biggest concerns about gas hydrates right now is not that they represent a resource, but rather they represent a hazard, particularly in the context of global warming. Okay. Now, when you look at future demands, both for demand of energy and supply of energy, there are several things that are consistent. This is a Shell oil projection suggesting that fossil fuels would peak around 2030. This is an APG projection suggesting fossil fuels will peak maybe around 2040. This is a BP projection suggesting they might peak in 2050. What they all have in common is that they're going to peak. And so, is there any way we can improve upon this? Can we increase the size of our energy resources, particularly our fossil fuels? Well, I listed a series of ways you could do that, and I more or less went through them, but what I didn't mention was energy conservation. Can that help? And the answer is not actually, not with respect to the size of the reserve. What it can do, though, by reducing the rate at which we're consuming it, we can extend the life of that reserve, and maybe more importantly, extend it to a point where we have economic alternatives, substitutions. Okay. But let's look at the other side of that curve. What about consumption? Can we bring that consumption down? And the reality is we have been. If you look at energy consumption, which is the blue line, and population, which is basically going to be proportional to the red line, we predicted back in the 70s that that red line would be what we're going to consume. But in fact, we're consuming almost half less than we would have expected. And that's because our energy use per capita, and more specifically, per dollar of GDP, basically as measured by our economy, has actually been reducing, has been shrinking, especially our energy productivity, if you like, with respect to GDP. So we're becoming much more efficient. We've had a huge decrease in energy with respect to lighting and computers, heating, refrigeration. The only thing that's kind of working against us are TVs, and there are some other things as well. But the reality is we've become much more energy aware, energy conscious. And for a variety of reasons, we are consuming less energy, and therefore we have at least some hope of shrinking that gap between projected demand and projected availability. Having said that, if you look at the energy per person relative to us in the U.S., most areas are relatively flat until you get to China. And what you see with China beginning in about 2000 was this extreme increase in per capita income. Per capita use of energy. India, less so. Africa, a lot of uncertainties in Africa. But what's clear is that no matter how efficient we are in the U.S., we still are part of a global community with respect to energy demand and availability. And if we don't think that China is of a concern, one of the areas that's extremely important is that the Chinese now are competing for resources in other countries that we're competing for. Because even if we do become self-sufficient in certain types of energies, we're going to be competing with other resources, be they rare earth elements or diamonds or whatever. Okay. One of the ways, though, that we have been extremely productive in reducing energy has been with respect to automobiles. And one of the reasons is there was a lot of room for improvement. Only about 12% of the energy that moves your car is from that barrel. Or better said, that barrel loses 88% of its energy. How does it do that? Well, you got to get it to the pump. You got to get it from the pump to the car. There's a lot of energy loss in here. And so a lot of work is done increasing energy efficiency. And that's been driven not to any small extent by government regulations requiring fleet efficiencies. And so the fleet efficiencies, if they were unchanged, this was a little old, but it gives you an example of how effective different changes are. If it were 24 miles to the gallon for a fleet efficiency, we'd be using almost 9 million barrels a day. Increase that to 34, we're down to 6. 39, we're here. Okay. 44, we're here. Well, we're getting increasingly high fuel efficiencies, and it's predicted that we may be up to 50 miles a gallon for car and light truck fleet efficiencies in the next 15 years or so. Having said that, that's going to be driven to a large extent by several factors, not the least of which is government regulations, because these things don't necessarily come because everybody wants a small car or everybody wants a car with a fill in the blank. And a lot of that will also depend on the economics of particularly electric cars, and a lot of that will depend on the economics of batteries. And so a lot of the projected decrease in use of petroleum is related to things like how good and how cheap are our batteries for electric cars. Okay, well, the problem with everything I've said is that they're all fossil fuels. No matter whether they're conventional or unconventional, whether it's gas hydrates or gasoline, they produce CO2 when burned. And they produce other things as well, all of which are air pollutants. And so the issue of how do we fill that gap with respect to fossil fuels that we're running out. Well, that's almost the good news, because as we run out of fossil fuels, we are running out of, or rather we're being forced to replace them with things that are of less pollution. And most of the pollution comes from transportation. These are non-point sources. These are our cars. Stationary fuel consumption, that's a point source, and think coal plant, think power plant, electrical generation. And then there's other sources as well. But our two main producers of air pollution are basically generating power and driving vehicles. Okay. Now, why is this important? Well, we know why. These are major greenhouse gases. But I should add that they're not the only greenhouse gas. There are a variety of greenhouse gases, actually H2O being the largest, but inasmuch as that's largely a constant natural factor, CO2 is about 50% of the greenhouse gas activity, methane 18, chlorofluorocarbons, the CFCs 14, etc. But I made a note here, and it's not in your notes, but I thought it was important to remind you that methane, which we've heard pop up in a variety of cases, is actually 72 more times effective, if you like, in warming the atmosphere than is an equivalent energy mass of CO2. Now that's over 20 years. Over 500 years, it remains 7.5 times more effective. That's in part because it's very long-lived in the atmosphere, and it's a much more effective global warmer or greenhouse gas. So although our focus in the newspaper and the like is typically CO2, we've got to recognize that in a lot of ways methane is even a worse problem. Okay. Where does the CO2 come from? Well, it certainly is mainly burning of fossil fuels, but it's also land clearing and then burning of the trees or the vegetation, and to a certain extent manufacturing and simply burning wood as a fuel. Okay, I don't have where methane comes from, but you know where a lot of it comes from, fossil fuels. It's also actually a major source from cattle feces and rice production. So methane has a lot of sources, just like CO2, and they are to a large extent important sources, and if we try to reduce it, we've got to figure out how we do that. Okay, we've known since the early 50s that CO2 in the atmosphere, and this star reminds me to remind you that any diagram with a star on it is in the last set of notes, that CO2 has been increasing. Okay, it's been increasing both based on direct measurements and ice core measurements. We can actually bring down, look at that increase in the rate of CO2 in the atmosphere, coincident with basically the Industrial Revolution. Okay, here are direct measurements, 2005 to 2017. That's basically expanding this, which actually kind of ends at 2005. So we see a continued increase, but we also see that we can use these proxy measures to get a sense of how much CO2 is in the atmosphere for the last 400,000 years. Now, what's important about that is that if we know the CO2 activity, first of all, we see it varies very systematically with the ice age or the glacial and interglacial periods. Okay, but what we see is that it's never been over 300 parts per thousand, parts per million rather. Until now, we're already at 405 parts per million. We are looking at records that not only have increased faster than any time, but higher than any time in the last 400,000 years. Now, this is a powerful graph because what it says is that this is unlike any natural phenomenon that's occurred on this planet in the last 400,000 years or longer. If that's the case, it has to be largely human activity. But of course, there's a subset of climate deniers that say, no, it's just a natural variation. So if this is a accurate record of natural variability, then we're way off in terms of denying this. So let's look at how this graph came about. And basically, it came about recording, getting both CO2 and temperature proxies from things that we can date. We can look at tree rings, for example, and we know that certain types of trees, they have annular rings, and we can measure their growth rates and relate that to climatic change. More importantly, we can look at ice cores. And as we drill ice, it turns out it also is layered. And each of the layers is a seasonal band reflecting seasonal changes in snowfall. And we can there sample the dissolved gases of the atmosphere. We literally have little samples of the atmosphere. And we can date them. So we can look at not only the amount of CO2 in the atmosphere of the North Pole 200,000 years ago or 400,000 years ago, but also methane and sulfur, etc. This is very powerful. Corals take CO2 from the ocean, incorporate it within calcium carbonate. They also, some, are very long-lived and have annular bands, and so we can sample those and go year by year. Lastly, pollen records can help as well. These are all either direct or indirect proxies of CO2 and or temperature. Okay. So using those proxies, we can, and other types of information, we can look at the evidence of climate change and decide, is there any reason for denial? We're going to look at rising sea level, rising temperature, warming of the oceans, shrinking of the ice sheets, shrinking of the Arctic sea ice, and shrinking of glacial ice. So let's look at those. This is the static rise in sea level based on tide gauges. Now the problem with tide gauges is that we need to be able to subtract out what other changes of relative sea level there are to get a eustatic change. So it's a complicated one, but we can get at least a direct measurement. But then one of the arguments was, well, you know, these aren't accurate. Satellite data, that's what you need. And so the good news is that the satellite data, which we've had from about 1993 to 2016, show a continued and similar rate of change. And so we know the sea level is changing, and we know that in spite of inherent problems with land-based tide gauges, we know this definitively from the satellite data. Now, the real question, see, here's what we have to date. So the real question now is, where is it going? Okay, and there are a lot of different models, and they're all based on certain assumptions about how much CO2 we're going to put in the air, which is based on assumptions about how much fossil fuels we're going to use, etc., etc. But you see there is a range in here, and then there's a much higher range here. And so you're looking at a sea level rise of between 10 and 35 centimeters. That's about a third of a meter in the next, well, actually 10 years or 15 years. That's actually a lot. It's a lot because a relatively small rise in sea level can have a huge impact on coastal regions. some regions because simply they're very low. We talked about that. We talked about the loss of marshland in Galveston, how a subtle rise in sea level will result in a lot of loss of highly productive marshland and land in general. The Maldives Islands are already disappearing under the rise of sea level. And as sea level rises, the erosion associated with storms increases as well. And so it's not just those areas that are being submerged by the rise, but those areas that are being eroded by the increased wave activity. Okay. We also have a similar issue with surface temperature. We've been measuring surface temperature from surface stations since 1880. Well, actually before, but globally, we've had a pretty good record since about 1880. And those records, this is through about 2005, suggest it's been increasing. Well, again, the critics would say, oh, there's all sorts of reasons that's not a good measure. We're looking at stations that are all over the world, but not necessarily representative of the whole world. Certainly there's nothing about the oceans, and we know that there are things like urban heat islands that are heating up areas around cities, so that's just not going to be very good. But then we went into the satellites, and so we started looking at, this is looking at land and ocean temperatures, and in particular, we're getting information from the satellite data now, and we're beginning to see that the increase based on land we can also follow based on ocean temperatures, and we can actually look at a global average. We can look at land temperature rise, ocean temperature rise, and then global temperature rise due to our ability to measure the satellite data. Okay. Now, going to the proxies, this has been the real biggie because now we can get estimates of temperature because it turns out that the isotopic composition of the oxygen that we're getting trapped in the ice or in the atmospheric bubbles within the ice is a function of global temperature. And that means that we can not only look at the amount of CO2, but we can also look at the oxygen isotope ratios, and from that calculate temperature changes. Now there's a lot of variability, but if you look at the averages, we're looking at the last 1,000 years. And so again, nothing has occurred in the last 1,000 years for temperature that's comparable to the rise in temperature we've seen. The Arctic sea ice is shrinking. The good news is we may have now a new inside passage, or rather a Arctic passage for an open seaway, but it's been shrinking substantially at about 13% per decade. If we look at the Antarctic ice mass, it's been shrinking since 2002 when we've been measuring it closely with satellites, as has the Greenland ice mass. So the point about the sea ice is that's a measure of warming, but it doesn't impact sea level. The Antarctic and Greenland ice mass is basically on land, and as it melts, it is contributing to a rise in sea level. And so much of the concern with respect to the melting of glacial ice, be it continental glacial ice or other land-based ice, is the rise in sea level. In fact, if you look at the global change here, and this is loss, I wish they had done it the other way around, but we're looking at very high rates of continental ice sheet loss since we started measuring in satellites. This is the cumulative decrease in global glacial ice, which includes the mountain ice as well. Okay, so we're looking at a loss of about 2,500 cubic miles of ice. So no matter how you look at it, we have had a steady loss of ice since 1960, And in fact, depending on where you look, we've seen this melting of ice really since the beginning of the 20th century. Okay. Now, one of the arguments goes back to, are you sure this can't be natural? Why does it have to be anthropogenic? Well, one thing we know is that there are variations in solar insolation. And so we do know that climatic change, and particularly those big cycles, those 100,000-year cycles, are being driven by changes in incoming solar radiation. Okay. So why couldn't that be the reason? Well, the problem is we can look at the energy that's been coming in from the sun, and yes, it has been varying, but if we look at the temperature variations, we might well be seeing that signature, but there's a far more important signature that's superimposed on any effect of sunspot activity. What about volcanoes? We know that volcanoes can cause global cooling, so that's not going to help a whole lot, but volcanoes certainly are an issue. Volcanoes also put out sulfates, which can result in cooling. Well, we can plot those. We can look at the effect of sulfates and volcanoes, solar activity, ozone, and greenhouse gases. And we can put them all together, and we can create a global climate model, or actually many global climate models. And the models are basically in here. And the observed is in but. So we can do a pretty good job of reproducing the observed climatic change in temperature, taking into account natural and anthropogenic variables. Okay, and it looks pretty powerful. Now, I will say this. When you do that, the total anthropogenic component is to increase it by this much. The biggest problem we have is that we don't really have a good way of determining things like the impact of clouds. Okay, huge standard deviation from clouds. And so what you'll hear by critics is, well, yeah, there are models, but there's a lot of unknowns. Yes, there are. There are models, but what about clouds? Yeah, we're working on that. And the bottom line is the climate deniers are denying the models, which they say are faked, but the problem is the observations really are pretty clear. This is one of those cases where we talk about a scientific fact. And then the argument is, oh, well, you know, they say 97% of scientists support the idea of anthropogenic change. That's just balderdash. Well, actually, that's true. That's not really the best way of saying it. 97% of qualified scientists, that is PhD level scientists doing research in global climate change, do support anthropogenic change. But so does the Geological Society of America, the American Geophysical Society, the National Academy of Science, the American Association for the Advancement of Science, the NASA and NOAA, of course, and globally, basically, the American Meteorological Society as well. The professional organizations that have the professional earth scientists, and in a broader sense, the scientific community as a whole, do support the idea, which makes it all the more frustrating because much of what we talked about in this course has, with respect to trying to mitigate potential environmental impact, is based on regulations and based on concerns that are being denied. And so these are things that we have to think about. This is a model that just takes into account natural forcing. This is a model that takes into account both. Okay, you have to attack the model because the interpretation is clear. There's no question from this interpretation, and this model can be applied to land and ocean surface, just the ocean, just the land, and of course heat content. One of the big criticisms early on was that we don't know what the oceans are doing. The CO2 we're putting more CO2 in the atmosphere than we're seeing a heat rise. Clearly your models are wrong. Well, sure, yes, they were. We had to figure out how much of the CO2 was being sequestered in the ocean. Turns out a lot of it. Oh, and by the way, that's causing the oceans to become acidic, which annoys the hell out of corals. So there are a lot of things that we need to recognize that with any science, it's never 100% true. But we try to reproduce the observations and explain them to the best of our ability. And I think we've done a pretty good job. Okay, what do we know? Atmospheric CO2 is increasing due to human activity. CO2 is only one of the greenhouse gases. And global temperature is rising. There's no question. We don't know specifically how much these are causing global warming. There's these anthropogenic effects, though we've got very strong evidence that it's the dominant source. It's a little harder to even say how global warming is impacting global climate. Some areas are getting hotter, some are getting colder, some are getting wetter, some are getting drier. The interrelationships of temperature that drives climate is very hard to predict. And what can we do about it? And maybe better say, what will we do about it? What are we willing to do about it? Is it worth it? And of course, it's not worth it if you don't think it's happening. And it's not worth it if you think global warming is good for you, which is one of the new tacks. Oh, well, you know, when times are good, times are good when the climate is warmer. Everybody likes it warmer. Well, it doesn't take long to think about how that's kind of a silly argument, but you're hearing it as well. Okay. Well, let's assume that CO2 is bad, and let's assume that our reliance on fossil fuels is going to have to change for a variety of reasons, including limited amount and environmental consequence. Where do we go? Well, we got a lot of uranium. That's a possibility. So nuclear is a possibility, and then the renewables. And renewables include this list of things. I'm not going to talk about tides. I'm actually just going to briefly talk about some of the others. But again, going back to anybody's projection, be it Shell, they basically see that gap being filled with nuclear and renewables. The APG sees that gap filled with nuclear and renewables. Okay. Now, interestingly, the relative mix differs. The APG saw nuclear being a lot more likely to fill that gap than, say, Shell did. And again, these are based on different times. And ignore the dates, because the dates really are not as relevant to this question as are the shapes of the curves. We're going to have a curve for fossil fuels that will get increasingly unable to meet projected demand. And that gap has to be filled with these things. And to what extent that reduction in fossil fuels is the result of availability and technology and economics versus environmental issues, who knows? But we have to fill that gap. Okay. Here's BP's projection. Again, that's only through 2035, so they're looking about here. That BP is a 2017 projection, by the way. And so again, they're looking at nuclear, hydroelectric, and renewable. Okay. So what are we going to do? Right now, those produce about, even now, not just 17 years ago, about 20%, about 10% for renewables and 10% for nuclear. Okay. Now the problem with nuclear is that it's dangerous. Okay. It doesn't produce CO2. That's the good news. But the thing is, even though, yeah, in terms of this is term, not sure when that was, but even though at one point, almost over 2/3 of our non-carbon generating electrical generation was nuclear, we haven't had any plants built since 1978. And so that has some important consequences. Basically, it says that our ability to produce nuclear in our capability, okay, is going to be dropping and dropping substantially if we don't either build new nuclear plants or expand existing ones. Okay, this was one of my favorite articles out of the Houston Chronicle in 1994. That's Mr. Plutonium, or Mr. Pluto. He's drinking some plutonium-laced water and saying, it doesn't hurt you. Of course, it turns out it's highly radioactive, and ingestion of 1/10,000th of a gram can induce cancer. But plutonium is what's used and what's generated in breeder reactors. Okay, the problem with breeder reactors is this plutonium, because a breeder reactor creates its own fuel. It creates plutonium that you can then burn. Well, we've realized for a long time that plutonium is bad. It's bad in part because it's highly radioactive. It's bad because it has a very long lifespan, but also in terms of nuclear proliferation. It's the thing you worry about when you worry about a dirty bomb, or when you worry about radicals getting a hold of nuclear material. And so for security reasons, almost nobody is trying to use breeder reactors. It's just not economic, and politically it's unstable. By 2006, you only had India, Russia, Japan, and China. Europe had shut theirs down. We've shut ours down. And of course, Japan, although in 2006 they felt quite confident about breeder reactors. In 2011, they had 3 meltdowns at Fukushima for reasons we've talked about, and that's all shut down. And so the future of nuclear is really in question. And it's not just the meltdown, the explosions, the destruction of large areas and large numbers of people. It's also things like radioactive disposal. We got to figure out how to dispose of waste that may be radioactive for 100,000 years. We actually have been disposing a lot of it at the Hanford site, which is a DOE site in the arid portion of Washington State. But basically, we're getting groundwater contamination, and this is that plume that has been leaking from these storage sites and has now entered the Columbia River. This is an old slide, but you can only say that it's only going to be worse the longer it sits. So the issues of where do we store it, how do we store it, are sufficiently controversial that the safe extrapolation is to assume it's not going to be filling that gap. Okay, too bad. It's virtually inexhaustible. There's no carbon, but between the waste, the meltdowns, and nuclear proliferation, it's going to be a very hard sell. Well, that only leaves renewables: hydroelectric, wood, biofuels, wind, solar, geothermal, waste, etc. So let's look at those in a little more detail. Renewables are thought to increase from 13% to 18%. Nuclear decreased from 19 to 16%. In reality, hydroelectric is going to be more or less constant. That's because we just don't have any more places to dam that are really big. and there are just a lot of environmental costs with building new dams, and we've talked about that. Everything else is increasing. Okay, biomass, geothermal, solar, and wind. Okay, so let's look at each of those a little more carefully. These are just, again, this suggests, well, no, this shows that there was a big increase from about the late 50s to about the mid 70s with hydroelectric. And since then, it's been more or less stable and will be stable for the future as well. Okay, here's that stability. And take a look at wind increasing. God, wind looks pretty good. In fact, here's wind. Okay, so we're going to come back to wind. But let's look at geothermal first. It's kind of the geologist's dream, energy from the earth coming in. And it's actually a major source of electricity for Iceland and New Zealand. Ironically, the world's largest geothermal development's in California. Okay, the geysers. But when you look at where it might occur, basically it's going to occur in areas where you have high heat flow. Not a surprise, but that means tectonically active areas. Okay, and so there are limits. There are these little dots are already identified hydroelectric, hydrothermal sites that we're looking at. One of the problems that we have is that in some cases, and I'll take Yellowstone as an example, it was suggested and even at some point maybe even permitted to try to have hydrothermal power adjacent to Yellowstone. The problem is that involves removing a lot of water because it's hot water, and you use that hot water to generate steam to run your turbine. And that affects the plumbing. And of course, the plumbing in Yellowstone affects the geysers. And so anything that affects the geysers in Yellowstone is considered a bad thing for good reason. So there's a lot of reasons why geothermal isn't really going to be a big player. It's not particularly economic. There's a lot of issues with water, and so geothermal is not going to be the answer, but it'll be in the mix. It's clean, relatively clean, it's relatively cheap, it's ours, it's domestic, and it is renewable. You can't transport it long distances, like a lot of things. You have to generate the electricity on site, and it's also geologically constrained. I mean, basically, there just aren't many places where you're going to drill into hot water. Okay, there are a lot of places where the sun shines, and so one of the things we can do is collect water through solar concentration. I mean, collect heat by solar concentration. Basically, all these mirrors are concentrating the heat at this particular point, and instead of just collecting the heat, maybe we ought to actually directly convert the heat to electricity. And so that's really what the photovoltaic end of solar energy is all about. We have your solar panels, and you convert it to electricity on the spot. And that can be at a municipal level, or it can be at a house level. Okay, and so photovoltaic cells are getting cheaper. There's a lot of areas where it shines a lot, and so clearly one option is to use photovoltaics as a type of solar energy to generate electricity, which can then be transported to other places. Okay, the sale has been going up as the prices are dropping, and the prices are dropping in part because of subsidies, but mainly because of technology. We're seeing a tremendous improvement in the efficiencies of these solar cells. And so that's making solar energy more competitive. It's still expensive with current technology, but it's getting better. Again, it's not portable. It is geographically limited, though not as limited as geothermal. But again, it's domestic, renewable, and clean. Okay. Interestingly, the new electrical capacities installed. That is, electrical generation units that have been installed in 2014, mainly solar and wind. And then natural gas, not quite sure what others are, no coal. We just don't see coal in the future in terms of new plants. Certainly we've got a lot of coal being produced and generating electricity in old plants. But it's what's coming in the future, and clearly the bets are solar and wind. Okay. Well, wind, of course, is another source of solar energy. Wind is being basically atmosphere moving from areas of high heat to low heat. And if you look at this diagram, boy, it looked good. Growth in U.S. installed wind power from 0 in 1980 to almost 5,000 megawatts. And then you get this, and they say, oh, well, look at that. It's slowing down until you recognize that that curve here is this curve here. And scale is really one of these interesting issues when you start looking at graphs. You can have a vertical exaggeration or not. And so it's always useful to kind of think about how this graph and this amazing acceleration actually is dwarfed by the acceleration of wind energy capacity. And then if you look at this for 2017, this is what's projected for through 2040. So we are right now at about a little over 200 gigawatts or billion kilowatt hours, and we're going to more than double that. So that's going to be a big portion. In fact, we'll be generating more energy by wind than any other renewable resource. Okay. And Texas is the leader in that, so it shouldn't surprise us. Wind resources, well, it's interesting. There's a belt right along in here, and it turns out that belt is essentially the areas of high winds. I didn't quite know that, but you can actually go to a website that shows what the wind velocities are for any day. This was September 9th, 2012, but basically you see that zone of high wind is the zone of high wind resources. And of course, that's where we're putting most of our wind power. Again, it's domestic, it's renewable, it's clean. It's expensive, but it's getting a lot less expensive. It isn't presently competitive. Again, it's not portable, geographically limited. These wind fields take up a lot of land. They're noisy, they're ugly, birds don't like them. But, bless you, on the other hand, they generate a lot of power. And so we're going to see more and more reliance on wind. Okay. Biomass, I also added these. If we look at the biomass resources, it's kind of interesting. It's over here, and there's some other areas as well. But you're saying, well, what's drawing that? Well, that's actually the Corn Belt. Okay, so let's look at how biomass generates energy. Well, the first thing you can actually just burn the biomass. Okay, generate heat right there. Okay, and that's done with respect to some municipal waste areas. There's also some areas in terms of waste that's generated by lumber. But the other thing you can do is let the waste decay to biogenic methane. Now, the methane we've been talking about for the most part is what we call thermogenic methane. This is the methane that results from the increased maturation of organic material with heat and pressure. Well, biogenic is essentially the swamp gas. That's the stuff that's coming off through decay today, and that's actually coming in landfills. And that's why you see these vents. Remember, we had vents that were venting the biogenic gases that were coming out of landfills. Well, why vent it when you could burn it? And that is exactly what we're doing. So we're generating electricity from what's sometimes called landfill gas or biogas. And so that's an important source. The one that's most important, though, is ethanol, where we actually convert crops such as corn or sugarcane to ethanol. And of course, ethanol is a biofuel. So now we can actually transport that by truck or by pipeline and put it in your car. A related transport fuel is from vegetable oils and animal fats, and that's biodiesels. So we can use crops or vegetable oils or animal fats, and we can generate fuel for our cars. And so that's really where most of the utility is coming. In fact, if you look at the increase in the rate of generation of ethanol, it basically started about 2000. And of course, this also is driven by government regulations. And the intent was to get more renewable resources. The problem, and there's some problems with this though. Well, let me just note that at present, most of that ethanol is from corn. Okay, and so this is the amount of corn that's produced, and this is the amount of it that's used for fuel. And so we're producing more corn, but we're actually producing less of it to eat or for animals or to export. Okay, so what we're seeing is a trade from corn as a food crop to corn as a fuel crop. Now, notice here, it's just kind of just thrown out, I'm not sure. Corn's the leading source of nitrogen pollution. Now, that's interesting. So let's see where we're going with that. Well, let's look first of all at how much energy it takes to produce a gallon of, or an energy unit, better said, of corn-based ethanol. Well, you get about 1.25 energies for 1 unit of energy put in. Now that's actually controversial because many studies say it's even worse. Many studies demonstrate that you use more energy to get ethanol energy from corn than you did if you didn't do it at all. So that is a huge problem. Okay, crop replacement's another major thing. We've seen wheat, sorghum, hay, cotton, barley, and oats all reduced. These are basically, why produce oats or sorghum when I can produce corn for ethanol and get a big subsidy as well? Okay. In fact, the subsidies are really important because it turns out that when we use corn ethanol to reduce gasoline consumption, 1 gallon, it costs taxpayers $1.78. Well, the short of it is that we may be talking about costs to the consumers of $16 billion a year in terms of subsidies and energy-related costs. Oh, and there's one other thing. The production of corn, especially, is the major source of nitrogen pollution and is a significant source of phosphorus solution, not only in the areas of the Corn Belt, but also downstream because it's draining all the way to the Gulf of Mexico. So what's going on here? Well, the problem is to get corn, particularly get it growing healthy, you need a vadose zone, a zone of unsaturated water, essentially depth to water table, that's deeper than many of the areas that they would like to grow corn. Okay. So what do you do if you have an area where you could grow corn but you can't because the water table is too high? Well, you put in a series of drains. These are called tile drainage systems. And what that does is it lowers the water table to allow you to produce the corn. Okay, and it does increase the yields, but it also results in an increase in nitrogen lost to the water, to the surface water. Here are maps of corn and ethanol production. Here are maps of the tile fields, and here are maps of nitrogen and phosphorus production. Okay, so we're producing corn, which is producing nitrogen, which is getting into the waters, which is polluting the soils and the waters. And by the way, it ends up creating or aggravating large dead zones in the ocean. Literally, the impact of ethanol from corn here is to cause major pollution and seasonal dead zones off the mouth of the Mississippi. Okay. Now, this is 52% of the nitrogens from corn. There's other sources as well. Only 25 from phosphorus, but still significant. Okay. So, is there a way of doing better? Okay. Well, there's a lot of biomass available if we're not restricted to corn. Okay, we've got large areas of the country, including the entire Texas Gulf Coast, that could have biomass produced. And one of the keys is using what are called energy crops. And so the idea is you use something that isn't used for something else, like food, that grows fast and doesn't require the same drainage characteristics. And so these are things like grasses, tall grasses, switchgrass is popular, or even fast-growing trees, poplars or willows, even chinaberry. Okay. And so they don't require a lot of fertilization. They can grow on less fertile soils, and they don't result in replacing other crops. They compete for land used as pasture as opposed to corn. They don't require much fertilizer. They actually increase the soil carbon. That results in less water pollution. And you can convert it to fuel or power without additional fossil fuel. I'll have to check on that. I'm not quite sure what they're getting at there. There also is another source, agricultural residue. That's the stuff that's left over when you harvest things like corn. And there you use the stalks and the leaves, wheat straw, and this is another way of increasing ethanol, but not taking corn away from other places. I'll also mention that the switch from corn as a food to corn as a fuel has global implications because it's increased the price of wheat to campesinos in Mexico. All over the world, this has had this impact. Okay, and of course, it's also being done in places like India where they're producing ethanol as well. Waste materials, we can think of a lot of ways where we generate waste that we could convert to ethanol. Forest biomass, it's suggested that tree topping and limbs collected can be done. The point here, though, is you don't want to cut down a forest to generate ethanol. And the reason there is forests capture a lot of carbon. But if there's a way of harvesting portions of that biomass, then you could use that as a bioenergy. Having said that, that's a more controversial source of biomass. So biomass and biofuels are going to be increasingly important, but hopefully they won't be corn, because corn was not a good choice. It is a politically very comforting choice to farmers in the Midwest and a variety of other vested interests. But biomass for fuels, a good idea. Coal for biomass, not so good. Okay. The last thing I'll mention just really briefly is, wouldn't it be nice if we had a fuel that when we burned it, the pollutant was H2O, which is a greenhouse gas, but let's assume that's not a problem, and energy. Okay. And that is, of course, what the hydrogen fuel cell is. You burn hydrogen and you get water and energy. Okay. The problem is, well, where do you get the hydrogen? Well, for that, you need energy. You need to add energy to water to get hydrogen to burn to get energy. So it's kind of a Peter and Paul thing, who you're going to rob, except maybe you could get the energy from solar energy, as an example. And then that solar energy is used maybe in Arizona or wherever the sun shines to generate the hydrogen, which is portable. Okay, so you could generate hydrogen on site, and then you could take that hydrogen and literally put it in cars. It's actually being used to generate energy in power plants. Right now, the main use is hydrogen as a byproduct of the refining of oil or hydrocarbons and also coal. And so we are using these hydrogen fuel cell technology to run some electricity, but it really hasn't gotten to the point of cars. And cars are really the main source of electricity that, or rather of energy that we're interested in. Okay, so that's all. I will have the notes. Does anybody have any questions before we leave? Next time I see you will be for the exam. Any questions? Yes, sir.
Covering the exam?
Say it again?
This material, energy.
Yes, that's what I meant by putting the extra part of the notes. What I post tomorrow will be those things from the last two lectures in addition to the previous lectures. Yes, ma'am. As soon as I can get them graded. We'll start grading on Tuesday morning, and I'm hoping to have posted by the end of the week.